Welcome to this deep dive into a fascinating corner of the mathematical world, the online encyclopedia of integer sequences.
The OEIS, yes, a fantastic resource.
It really is. And for our number theory students tuning in, today we're focusing on one particular sequence, A000213.
A personal favorite. It looks simple on the surface, but, well, it goes deep.
Exactly. The formula itself is very straightforward. AN is just the floor of n squared divided by 3.
That's it, though you might see it under older names too, right?
That's right. It used to be known as M2439 N0966 in older padlogs. Worth knowing if you're digging through older literature.
Good point. And the sequence starts at N0.
Yes, the offset is 0, with the fourth term listed being for N4. The sequence begins 0, 1, 3, 5, 8, 12, 16, 21, 27.
And it keeps going. The OEIS entry lists quite a few terms, up to 936, I believe, for the first 50 or so terms.
It does. But the really amazing thing, and what we want to explore today, is how this incredibly simple formula connects to just a surprisingly diverse range of mathematical and combinatorial ideas.
Absolutely. It's a perfect example of that hidden interconnectedness in mathematics. You start with floor N23 and end up, well, all over the place.
Okay, so let's start unpacking some of these connections. One that jumped out at me was Benoit Cloyder's observation about matrices.
Oh, yes, the determinant connection.
He found that for n greater than 2, an is actually the determinant of a specific matrix. It's an n2 by n2 matrix, Mn, with a pretty defined structure.
Right. The structure involves mostly 2s on the main diagonal, 1s on the super and subdiagonals, and zeros elsewhere, if I recall correctly.
Exactly. Why is finding something like this sequence as a determinant significant?
Well, it gives you a completely different lens, doesn't it? You move from simple arithmetic to linear algebra. Determinants carry geometric meaning, relate to eigenvalues, system solutions.
So it opens up algebraic tools to study the sequence.
Precisely. Maybe you can find properties using matrix theory that aren't obvious just from floor N23. It hints at some deeper algebraic structure.
Fascinating. Okay, let's switch gears a bit. Combinatorics. Ralph Steffen found a link to directed Cayley graphs.
Right. He found that AN is the largest possible size, the number of vertices, for a directed Cayley graph that has 2 generators and a diameter of n minus 2.
Okay, let's break that down a little. A Cayley graph visualizes a group structure, right?
Essentially, yes. Nodes are group elements. Edges show how generators act. 2 generators means you have 2 basic moves to get around the graph.
And the diameter.
That's the maximum distance, the longest, shortest path between any 2 nodes in the graph. So Steffen's result connects our sequence to how large you can make one of these specific graph structures while keeping everything relatively close together, diameter-wise.
So floor N23 puts a fundamental limit on the size of these networks.
Given that diameter constraint, yes, it links the sequence growth to a property of network structure.
That's quite neat. Another combinatorial link, this one feels almost visual, comes from Dmitry Kamenevsky.
The rectangle packing.
Yes, packing 1 by 3 rectangles, non-overlapping, into an n by n square. He observed that for n greater than or equal to 2, an seems to be the maximum number you can fit.
That one feels intuitive somehow, doesn't it? Dividing n squared by 3, 3 being the length of the rectangle.
It does suggest a connection. You're tiling an n squared area with pieces related to 3. It connects the sequence to geometric packing efficiency.
And I think he mentioned using a tool, Lobato's tool, for verification.
Yes, the OEIS entry links to it, so it seems computationally verified for many cases at least.
Which strengthens the observation, even if a full proof for all n might be harder.
Staying with graphs, there's a result from Yang about K4-free graphs.
Turin-type problems, essentially.
Exactly. Yang showed an is the maximum number of edges you can have in a graph with n vertices without creating a K4 subgraph.
A K4 being 4 vertices where every pair is connected by an edge, like a tetrahedron framework.
Right, so no little cliques of size 4 allowed.
And floor N23 gives you the maximum edge density under that restriction. It's a classic extremal graph theory result showing up here.
It really highlights how fundamental this sequence is, popping up as a bound in graph structures.
It does. Now, there are also some purely arithmetic properties, aren't there?
Yes, John Perry noted something interesting. If n is not a multiple of 3, then 3 times an plus 1 is a perfect square.
And if n is a multiple of 3?
Then 3 times an is itself a perfect square.
So the relationship to squares depends on n modulo 3. That smells like number theory, perhaps quadratic residues or something similar.
It definitely hints at deeper number theoretic structure related to divisibility by 3.
Which resonates with the divide by 3 in the original formula.
Indeed. And speaking of deeper connections, Peter Bala identified this sequence well, ignoring the very first term as something called an elliptic troublemaker sequence.
Right, Rn13 and Rn23 in Stange's notation, elliptic curves. That's some pretty advanced stuff.
It is. Can you give us just a flavor of why a sequence like ours might appear there? What makes it a troublemaker?
Well, very briefly, elliptic curves are defined by certain cubic equations. Studying their points, especially rational points, is incredibly deep. Certain sequences arise naturally in this study, and sometimes they exhibit, let's say, difficult or complex behavior related to the curve's properties.
So troublemaker is maybe an informal term for sequences that are tied to these complex aspects.
Sort of. It suggests our sequence plays a role in understanding the intricacies of those curves. It's another sign of its surprising reach.
Okay, back to slightly more, perhaps tangible combinatorics. Partitions. Colin Barker found a link.
Yes, partitions of 2n.
Specifically, ANN counts the number of ways to partition the integer 2n into exactly 3 positive integer parts.
Gus Wiseman gives some nice examples in the comments.
It says, for n equals 2, 2n is 4. The only partition into 3 positive parts is 2 plus 1 plus 1, and A2 is 1 matches.
And for n3, 2n is 6. The partitions are 4 plus 1 plus 1, 3 plus 2 plus 1, and 2 plus 2 plus 2. That's 3 ways.
And A3 is 3. It works out perfectly.
It's elegant. Counting partitions gives the same result as floor n23.
There's another interpretation from Gerhard Kirchner about non-overlapping triples in a matrix.
Along diagonals.
Yes, triples like ik, I plus 1, k plus 1, I plus 2, k plus 2. The maximum number of such non-overlapping diagonal triples you can find in an nxn matrix.
And that comes out to...
He gives a formula,
Yeah.
floor n3 plus 2 times the sum of floor k3 from k1 to n1, which simplifies to floor n123.
Which is very close to our an, just shifted slightly.
Yeah.
Related, definitely.
Anton Zakharov also proposed a conjecture.
Related to geometry. Sabians.
Yes, that an might count the number of intersection points when you draw n-Sabians lines from a vertex to the opposite side in a triangle in a way that maximizes the number of pieces the triangle's cut into.
Wow. Okay, that's connecting it to a geometric dissection problem.
Wow.
Fascinating, if true.
It links to another sequence, A000213, which counts the maximum number of pieces.
And another interpretation from Gus Wiseman again, this time about unimodal triples.
Right. He states an is the number of unimodal triples of positive integers that sum to n plus 1.
Unimodal meaning they rise to a peak and then fall or stay level, like 1, 3, 2, or 2, 1.
Exactly. For example, for A2, we need triple summing to 2 plus 1, 3. The only unimodal one is 1, 1, 1 and A2, 1.
And for A3, summing to 4, we'd have 1, 2, 1 and 2, 1, 1. Wait. Are repetitions allowed? Let's see his examples. 1, 2, 1. 1, 1, 2 is not unimodal. 2, 1, 1 is. 1, 1, 1, 1 isn't a triple. Need to check the precise definition there. But the examples he gives are 1, 1, 1 for A, 1, 2, 1, 2, 1, 1 for A3. Oh, wait, the sum is n plus 1, so A3 sum is 4. Triples are 1, 2, 1, 1. And also 1, 1, 2 is considered unimodal if we allow non-strict decrease. Let me recheck his examples. For N3, sum is 4. Triples 1, 2, 1, 2, 1, 1, 1, 1, 2. Yes, seems those are the 3. And A3, 3.
Okay, so it relies on a specific definition of unimodal there.
Yeah.
It's another combinatorial counting connection.
It seems so. There's also a generating function, of course.
Yes, Franklin Adams Waters and Michael Somos provide one. It's a rational function, as you might expect for sequences with linear recurrences.
Speaking of which, there are several recurrence relations known too, right?
Yes, quite a few. Alexander Burstein gives one. an plus an3, an4 plus 2 for NL4.
That's quite compact. It shows how terms depend linearly on previous terms, plus a constant.
He also gives an3 plus A000480 nas2, relating it to another OEIS sequence, the odd numbers.
And Richard Forberg found a different one. Aaron1, An1, An2 for N Ingle 2.
That one looks quite different, involving n squared explicitly.
Yeah, it's interesting how many ways there are to generate the same sequence.
There's even a sum involving the reciprocals, calculated by Enrique Perez Herrero.
The sum of one An converges. Seems plausible since An grows like N2.
Yes, he gives an approximate value for the sum from N2 onwards.
And a simple symmetry property.
Yes, Paul Kurtz noted that An pist An. It makes sense given the N2 in a formula.
Absolutely. And the page lists many cross-references to other sequences too.
It does. Sequences like A001399, related to partitions, A001353, related to central polygonal numbers, A004523, centered square numbers. Exploring those links could be whole other deep dives.
Definitely fertile ground for seeing more connections.
And finally, for practical use, the entry provides code snippets.
Maple, Mathematica, PARI, Magma, Python. Standard procedure for OEIS entries makes it easy to generate terms.
Right. So we started with this very simple rule. AN is floor N23.
And we found it hiding in determinants, graph sizes, packing problems, graph colorings or edge bounds, number theory properties, partition counts.
It's really quite remarkable. The breadth is just astonishing.
It truly is. It makes you wonder, doesn't it? What is the underlying thing, the fundamental principle that makes this specific sequence, floor N23, appear in all these seemingly unrelated contexts?
That's the big question, isn't it? Is there some deep structure we're only seeing glimpses of through these different windows?
Perhaps. Or maybe it's just a fundamental density or growth rate that manifests in various combinatorial and geometric settings. It's something to ponder.
Definitely something for our listeners to think about. And of course, if you want to explore all these connections in more detail, check out the OEIS page for A000213. All the references and links are there.
It's an invitation to explore the beautiful web of mathematics.
Couldn't have said it better myself. Thank you for joining me on this exploration today.
My pleasure. Always fascinating to talk about the OEIS.